Well, fortunately, I think our next speaker needs no introduction. So Pamela will continue with the lunar water distribution.
Thank you.
Instrument development.
Okay, so do I do this or do you put it full screen? I do? You'll do it or I'll do it? Thank you. Great. So I'd like to talk to you today about a concept that we've been kicking around at Goddard for the last couple of years. We were thinking about some of the really essential science questions that we could potentially answer about on the moon, and of course water, and there are a lot of folks involved with LRO and we're involved with M3 at Goddard as well. So we thought that something that could provide us a really good handle on the systematics of water would be particularly useful. So this is kind of a backwards approach. We actually started out with a mission concept and then looked at the kind of instrument we would need to be able to perform the job. So I'm going to talk basically about both today, the LWaDi concept and the Birch's Broadband Infrared Compact High-Resolution Exploration Spectrometer, which is named after my favorite poem by Robert Frost, in case anybody in the room doesn't recognize that. And every child growing up in New England memorizes Robert Frost poems like Holy Scripture. So there's a lot of people involved with this mission, and only some of them are actually named here. So it's just really a partial list. And some of them are in this room, like McDowell and Farrell. So I don't really have to go over this, but in my talk, for your future reference, I have lots of rationales for why lunar cubes and why water on the moon. And so if you need any arguments like this or need to convince yourself at any time, you can certainly refer to this. But you know, as everyone else has said today, we really look at the moon as a gateway to the solar system, and a lot of the moon also as an analog for a lot of solar system processes, and also an ideal testbed because it has so many different kinds of environments, including some very difficult and challenging ones from a lot of standpoints, an ideal technology testbed. So solving the problems of getting around in the Earth-Moon system, the one remaining problem that is challenging that you can't solve as well is communication, because things are a little closer. But pretty much anything else out there is it's great testbed. And again, I'm not going to read this, but if you go through, as I have with a fine-tooth comb, any of the online documents for consensus documents for the planetary science community, you will find there is nothing mentioned about CubeSats, but there's plenty of ammunition for why we want to fly missions that can provide us with distributed measurements, and anything that will show us about the interactions between volatiles, dust, charged particles, and fields are particularly significant right now, and CubeSats are ideal for doing that. Though we are forced at this point to deal with CubeSats as pathfinders, as not where I think they will ultimately end up, because they are so ideal for multi-platform distributed systems. So we have to prove ourselves by being able to handle very essential, highly focused but essential science problems with often with a single instrument. I think we can make that argument for LWaDi and for Birch's. So the idea behind the kinds of measurements we want to gather here, which require us to look at sort of a near to mid-infrared part of the spectrum, is to be able to provide a context of composition in terms of what the regolith overall rock composition is, to help us to understand volatiles and also see distinctive features related to volatiles and regoliths. And we see regoliths like this. They're the most common type of surface in the solar system by far. The Earth's surface is not, but the moon definitely represents a very typical surface in terms of the interaction with fields and particles and what happens to volatiles, the temperature changes. And also to understanding the dynamics of volatiles in terms of where they go, how they interact, what form they're in, allows us to understand a crucial part of regolith formation, what's called space weathering, and I think potentially the role of organics and biological precursors as well. And these are in environments that we don't understand very well: extremely cold, extremely hot, a lot of radiation. So I believe that there's a Nobel Prize hidden somewhere, and anybody here who can really help to elaborate these processes, and observational evidence will be very much a part of that. This is one of my favorite pictures. It just shows you basically over on the right-hand side the ranges of temperatures for a lot of bodies in the solar system. Nobody can see that. That's right. Oh, you can see that. Oh, we can see the arrow now. Very good. And then these are temperature ranges in color associated with that. So you can see, especially as you approach the poles, there are all these little micro niches which represent different environments in the solar system where you can see the kinds of processes that are going on. Very different thermal conditions, very different illumination regimes. So it turns out to be the moon turns out to be a very interesting place. Now the concept behind the Birches itself, the broadband infrared instrument, is that it's the idea is to have a high resolution, high spectral resolution. It's actually 5 nanometers and not 10 nanometer instrument. We have now come up with a design that's even more compact than the one we started with. We are at about 1.5 U, assuming we can carry through with our idea for developing the very compact detector interface electronics. It's approximately 2.5 kilograms, and we're talking about overall probably 5 to 6 watts. We also have a compact cryocooler. And the idea is that we look in the area from about 1 to 4 microns. We actually have heritage from the OVIRS instrument on OSIRIS-REx and some other earlier broadband spectrometers. And in this particular spectral region, you can not only, there's some indications of this over here, you can look at major mineral bands for silicates and non-silicates to give a compositional context. A lot of volatiles, including water in its various forms, liquid water, ice, and vapor, also bound water and absorbed water. And all of those features are in there. So it's a very fruitful area to be able to look at. One of the key features also, and we started off this because we weren't sure how well we'd be able to control the attitude, because we wondered, well, what kind of attitude control system can we have, and what kind of onboard fuel are we going to need to carry? Will we need to do adjustments a lot? And what Dave Folta, Mr. Magic, he basically found this very stable orbit. We probably won't have to do very much with what's called station keeping to stay in orbit. But we have an adjustable iris, which is a unique feature that allows us to control the spot size so that we could use it basically to make the spot size the same regardless of our altitude for a very elliptical orbit, which is a very stable orbit, by over about a factor of 3 variation in altitude. But you could also use it to make something like narrowband and wideband. Basically, you can make a very small spot size. You could vary a spot size. You could look at a small area and the area around it if you wanted to do that. So it makes for a very flexible instrument. This was our original concept for Birches, just a description of the optical system. Aperture, 2 off-axis parabolic mirrors consisting of aluminum, very simple. Here's where the adjustable iris is, and a Mercad telluride detector with a linear variable filter. And when we design the electronics, we'll basically make it so that you can operate it either in exclusively very high resolution, spectral resolution point spectrometer mode, or an imaging spectrometer mode. And the only reason we're not operating it as an imaging spectrometer at this point is because of bandwidth limitations. But we will build in the flexibility into the electronics to be able to do that as well. And then we have a compact cryocooler also by Rycor. Their latest, actually they have something that's even later than the latest. They have something that's called the K562S short. It's shorter than the stubby. And it's very compact. And one of our biggest challenges is going to be to get develop these detector interface electronics that are considerably smaller in volume than the existing ones. And the idea is to develop the generic detector interface electronics package that will be available to other people who are flying similar spectrometers. Oops, didn't mean to do that. And this is the latest, basically. We just went through a design lab exercise and came up with a version of this design that's 1.5U rather than 2U. That we kind of know from experience will give us a lot more capability to build in redundancy for some of the processing capability we're going to need on board. So we like to liberate as much volume as possible so we can build in redundancy for the command and data handling functions. Some of the components. Just basically the detector array, that's an H1RG from Teledyne, which is very popular. This is what a linear variable filter looks like. It's sometimes called a wedge filter, and a tactical cryocooler from Rycor. And we want to maintain the detector itself below 140K, and that should be doable. Probably take about 3 watts. in order for us to be able to get the longer wavelength part of the spectrum, which is where we would have the most thermal noise. And then the big challenge, which is basically to maintain the optics box at below 240K. According to the thermal modeling we've done that should be possible. So we have to sort of build in a lot of time and effort to develop basically a thermal protection design with additional radiators to be able to maintain our optics box at 240K, maintaining the interior of the spacecraft in a nominal operating environment for electronics is very doable. That was not a major challenge. Even though the moon is very hot and very cold, we can maintain the interior between 0 and about 35K. Degrees centigrade. But maintaining the optics box at that lower temperature turned out to be a major challenge. I'm not going to go into that because some of the data is wrong. And this is kind of what our concept looks like. So we've got this is the spectrometer, batteries. We're basing this design on a design for the H-Tides Turtles mission concept that we submitted a proposal to H-Tides for. We will need, when we first started out, we didn't really think we were going to need a main propulsion system. We thought, well, we'll get dumped off into lunar orbit, and it'll be pretty easy to get to where we want to go from where we get dumped off. Not true. Actually, the hard part, and as Dave Folta will talk to you about tomorrow, you can get to the moon using weak stability boundary trajectories for maybe a couple hundred meters per second or less if you're willing to spend more time doing it. That turns out to be minor. The major part is getting from where you get, basically you get captured by the moon into your final destination orbit. And because we're doing a science mission, there are very specific requirements for the kind of orbit that we need. So one of the challenges of the flight dynamics folks like Folta to pass is getting us injected into lunar orbit in such a way that it minimizes the delta V we'll need to go from where we get injected to where we want to end up. So timing and getting, matching everything up. Unplugging and plugging from that weak stability boundary trajectory is everything, very complicated, and that's where all the cleverness lies when you do that kind of flight dynamics. The kind of orbit we want to be in, relatively high incidence angle orbit, extremely elliptical because that's a stable orbit, low altitude periapsis, get us down to about 100 kilometers over the illuminated hemisphere, and about 5,000 kilometers at apoapsis. And we spend 6 months, and we basically are in a locked orbit whereby we get to go back and revisit, for every lunar cycle, we get to go back and revisit the same real estate at a different time of day. And by doing that, we're looking at a variety of pieces of regolith at different latitudes and different times of day, going back over the same area, so we will be able to understand the systematics of water, what form it's in, how much there is. It'll give us some insight on exosphere formation and a lot of other things. And yes, when we did our calculations, I think we've underestimated here, but we come up with a total mass of about 10.5 kilograms and a volume of 6 with very little margin, a 6U with very little margin, and because we need to carry a propulsion system, the propulsion system is the major power hog. Fortunately, when you need the propulsion system, if you get shot out of into the EM1 of the upper stage, and you're in a heliocentric trajectory, you need the propulsion system and occasionally the attitude control system to do burns several times during your trajectory for periods ranging from hours to days. And those are the times when you will basically be using a lot of power. You'll need to keep the solar panels need to be gimbaled to be able to get you all the power you need. You're not going around the moon. You're not changing temperatures. You're basically, it's very stable, but that's the driver. So once you get into lunar orbit, you do not need to use the propulsion system in that mode. So that means you have a lot of power to spare, actually, which is a good thing, but the driver for the power is definitely going to be the propulsion system. Some of the challenges. Yeah, we've talked about some of them. I've alluded to some of them. So mobility and transportation. There are several potential solutions for propulsion systems for a variety of reasons. We looked carefully at the microcathode system that GWU is developing. It's small, compact, and inexpensive. Those were the 3 factors that went into it. And we're looking at it. It's very flexible, very scalable. So we basically are looking at something like the Turtles spacecraft will use, which will have two different varieties of thrusters, essentially, to do attitude control and to do main propulsion. And then there are attitude control systems, like the XB1 provides basically all the components of attitude control we need, plus a bus with some of the controllers on it. So we'll use that, plus some redundancy and some other command and data handling functions. So there are solutions out there. I believe that what the EM1 opportunity is going to do is going to push forward the propulsion systems and test them, because they're essentially all flying, all 11 of those slots. Those people we're all going to be flying prototypes, and I think that probably most of them will use propulsion systems. So in a few years, we'll have tested propulsion systems, and the launch is supposed to be nominally in 2017. Thermal mechanical is a special problem for the moon. It's often undervalued and underrated as a serious issue by people who do design. Okay, so it's time for questions, so I can move on. Okay, power generation, not a problem. It's all basically to support propulsion. Then you have a lot of extra propulsion. COM is a problem. We need more COM. Courtney's going to talk about that tomorrow. We have an X-band system that JPL developed for Inspires, and I think all of us probably are going to be using that system. And autonomy would be particularly helpful, as we discussed earlier today, when we start talking about distributed concepts. And that's a short list, a very short list, some of them mentioned in this room, of some of the Cubesat concepts in various levels of development that are somehow connected to this meeting. What have I got for the last one? Oh, I'm just going to leave this up. So we'll talk more about these things in the course of the design challenge. Are there any questions? Yes.
Hello? Oh, it's on now, yeah. So what would be the duty cycle of the spectrometer?
Okay, so we have basically a 7-hour orbit, and we're basically taking data for about half an hour, so that's data taking mode. And then we're doing, in order to, since our plan will probably be to use the Moorhead station, the Moorhead 21-meter X-band capability, because it'll be accessible to us as opposed to the DSN, which is much harder to be able to get. We'll be doing COM over about 6 hours during the course of a day. So we basically have 3.5 hours a day, get something on the order of 25 megabytes per is it orbit or day? I can't remember. But in any case, we will require about 6 hours. But there's good parts of that, because that means that we'll be trackable for that period of time, which means we should know our position pretty well. And Moorhead will have all of the, they're going to be a DSN backups station, so they will have they'll do all the protocols, they'll have all the software. So we on the ground will do our final solution for our actual position. We'll have predictions, and we'll basically use those. And on the ground, we'll do the actual determination of where we were specifically. So that's the plan. Yeah. That's to get around, the big challenge, which is basically bandwidth. It's a major issue, even with the X-band system, which theoretically, using the 21-meter, we're talking about something on the order of 10 to 12 kilobytes per second capability, which is why we require a long downlink time.
Maybe I'll just briefly share the community. The DSN organization is fully aware of the needs of the small satellite community for that capability, and they are working mechanisms to make that available.
Well, we look forward to the possibility of compact laser-based systems, which should give us a lot more. We just need lasers. We just need laser ground stations, basically, to support that. We decided against a. Did you want to say something, Jeff? I don't know if you were raising your hand. We decided against a high gain antenna because it's just it's just huge, and it makes the spacecraft, calculating moments of inertia and doing the attitude control stuff a lot more challenging. So we decided to go with the dual patch X-band antenna system and the IRIS that JPL developed. I guess we're done.
Okay. Thank you, Pamela.
You're welcome.